eager to share with you, with our panelists today, their perspectives, their insights, and create kind of an interesting discussion about what the broad potential of fast reactors looks like, why fast neutrons are so promising as a fundamental enabling technology source, as demonstrated by the spectrum of technologies and developers represented here, and kind of a glimpse of what the future can look like with a fast reactor powered world. So with that, we'll go ahead and get started with introductions. We've got some exciting participants for joining us today who will be also making some exciting announcements as this goes forward. So with that, I'll go ahead and kick it off to Jeff, if you wouldn't mind introducing yourself and giving the quick few-minute introduction to what you guys are up to.
Happy to, sure. So I'm Jeff Latkowski. I'm a Senior Vice President at TerraPower. Been with TerraPower now for a little over 8 years, and prior to going to TerraPower, I was with Lawrence Livermore National Laboratory for a total of about 21 years, where I worked almost entirely on laser inertial fusion. So this is pretty different shift when I went to TerraPower. Easier in a lot of ways. And TerraPower, of course, is pretty well known for the traveling wave reactor. I got to TerraPower in 2012, and actually I've never worked on the sodium fast reactor. Instead, I was specifically tasked with finding additional projects for TerraPower. And as I learned more about the traveling wave and SFRs in general, you know, I liked some of the nice features, and basically, given my prior experience in fusion, I had a fair amount of molten salt background, and I asked the question, you know, hey, can I make a molten salt do that too? And the answer turned out to be yes, as long as I was willing to go to a fast spectrum. In fact, TerraPower, I should note, had considered molten salt reactors back in 2007, 2008, and rejected them because it was sort of, you know, your father's classic molten salt reactor, in that it had a thermal spectrum, graphite moderator, and a heck of a lot of online processing. And it was those things that TerraPower didn't like. And then by going with a fast spectrum and a chloride salt, we were actually able to avoid those things for the most part. And so it makes for a more attractive option that can do things similar to what the traveling wave reactor can do if that's what we choose to do. And so that's kind of how I got to TerraPower and how TerraPower got into fast spectrum molten salt. Maybe I'll stop there for now.
Great. Thanks, Jeff. Appreciate that.
Certainly.
That's excellent. All right, so Don, you mind kicking off your story and kind of your background in this?
Thank you. I'm Don Wolf, pleased to be with you on this panel. I'm the CEO and co-founder of a company called Advanced Reactor Concepts, known more generically as ARC. ARC is developing a 100 megawatt sodium fast reactor, which we call the ARC 100. Liquid sodium is the coolant, and a metal alloy of uranium is the fuel. The ARC 100 proprietary core design enables a 20-year refuel cycle. With fewer shutdowns for refueling, the reactor's utilization rate is maximized and reactor operations simplified. Also, our deployment in developing markets will have a trusted third party rather than the operator control access to all new and used fuel. The long fuel cycle will be a true competitive advantage for export into the developing world, we believe. What are the other advantages of this design? First, the ARC 100 offers exceptional inherent passive safety that derives from the interactive physics of the sodium coolant, the metallic fuel, and the ARC proprietary core design. If the ARC 100 loses electric power or faces any other accident sequence that leads to overheating, the heat rise triggers negative reactivity and a gradual cool down to a safe, steady state with no damage to the reactor or its fuel. This safety performance was conclusively demonstrated by the EBR2 prototype for the ARC 100. And I'm pleased to note that a film of this 1986 safety demonstration is available on the ARC website, and that the ARC Chief Technical Officer, John Sackett, actually conducted the experiment. The second advantage of our design and of fast reactors generally is the ARC 100 will breed new fuel as it operates, and its fast neutrons will allow fission and recycle of actinides. As a result, with a proven chemical separation process that does not separate out plutonium, nuclear waste can become new nuclear fuel, substantially simplifying waste management. The third advantage, and a very important one, is the ARC 100's inherent safety enables a simple design without expensive add-on redundant safety systems. And the goal is energy generation that can compete economically with natural gas. The fourth and most likely most important advantage of our SFR design, along with 3 other developing companies, is its technical maturity. ARC with 3 other companies have the same grandparent. The EBR2 prototype that operated successfully for 30 years at the Idaho National Lab. Senior engineers from the ARC2 team are officers of ARC. What is our path to market? We have focused on Canada for initial commercialization and have entered into agreements with the first customer, New Brunswick Power. ARC and the customer are now cooperating in the Canadian regulator's vendor design review process and have completed phase 1 of this process in 2019. We of course will focus on the US and other markets. The US is dependent on the pricing of energy becoming more realistic and the regulatory environment becoming more feasible, both of which are likely to happen in the near term. With that, I'll stop and wait for questions as they come. Thank you very much.
Thanks, Don. Appreciate that. Next, we'll have Paolo go ahead and talk about what they're up to.
Okay. Yeah, good afternoon. First of all, thank you for inviting Westinghouse to the webinar. I'm definitely glad to be here. My name is Paolo Ferroni. I'm the technical lead for the Westinghouse-led Fast Reactor program, which means that I basically oversee all the technical activities pertaining to the LFR, both domestically and internationally. I joined the company, Westinghouse, back a little bit, I think 11 years ago, straight out from MIT, where I met also Jake, and we overlapped for quite some time for our grad studies. I think the passion for fast reactor probably had that origin. The first couple of years or 3 years at Westinghouse, I was involved primarily in light water reactor research and in support to AP1000, but I quickly transitioned to advanced reactors and non-light water reactors specifically. Starting in 2015, which is when the Westinghouse LFR program started, I became the technical lead for the program. 2015, we performed an investigation across multiple technologies, including both generation 3, 3+, generation 4, and even some, I would say, generation 5 technologies that you can more likely see on Wikipedia than technical and journal papers, to basically investigate and explore whether there is a technology that can have good potential for essentially economic competitiveness. And so this is when and this is how the Westinghouse LFR program started. In Westinghouse, I work in the, it's called the Global Technology Office, or also known as Innovation Organization. Is a quite sizable organization within Westinghouse, which is tasked to essentially have the responsibility to bring innovation to nuclear across the spectrum, which means either innovating single components, materials, but also processes or modeling simulation tools, and even much broader entire reactor concepts. And this is where the Westinghouse LFR position itself within the innovation organization, together with the rest of the reactor concepts and reactor designs that represent the portfolio for Westinghouse, AP1000, eVinci, LFR, and also light water SMR collaborations. And I think this is pretty much a good overview about my background and my story with LFR.
Great, thanks, Paolo. That's excellent. I appreciate that. Yeah, and now we'll end it off with Ron before we jump into kind of the broader dialogue. So take it away, Ron.
Thank you. Last but hopefully not least, thank you very much, Jake and everybody on this distinguished panel for the opportunity to talk to you. I'm the Senior Director of Strategic Development for General Atomics Electromagnetic Systems, headquartered in San Diego, La Jolla, beautiful place over there, and the surroundings. I have joined GA about 3 years ago after many years with the National Lab System at Argonne National Lab specifically. My first job was with the IAEA, actually, that brought me into the nuclear field back when, I'm not going to say when. And I had a couple of stints in DC working for the DOE, ARPA-E specifically, and the Senate Energy Committee for Senator Lisa Murkowski, the chair of, then the ranking member of the Energy Committee. So I'm very pleased to be part of the private sector now, joining my fellow participants here. General Atomics has a long history and experience with reactor design and construction, especially integrating innovation into all that we do. Befitting this occasion of a discussion on the many advantages of fast reactors, we at General Atomics are excited to announce that we are developing a new 50 megawatt electric reactor we are calling the Fast Modular Reactor, or FMR. We're doing so in collaboration with our partner Framatome. GA's and Framatom's combined decades of experience in the civil nuclear domain and broad capabilities will assure the successful development and deployment of this groundbreaking reactor. The General Atomics 50 megawatt electric fast modular reactor is truly intended to be a community-friendly, safe, and distributed resource for the mid-2030s US power market, when we believe demand for such new generation will be spiking across the country and the globe for that matter. We designed this plan by being customer driven. That's really important to us. It is an electric power plant that will give the customer what the customer wants. Our goal is to not to focus on the fact that we are developing a nuclear reactor per se. Our goal really is to make a 50 megawatt electric power plant that provides safe, carbon-free electricity capable of incremental capacity additions. That's very important. It's just an added benefit that it's a fast reactor. The FMR's modular design allows for it to be factory built and assembled on site to keep the capital costs low, while the use of dry cooling facilitates siting to complement renewables in nearly any location. It is also ideal for end of transmission line needs, alleviated grid congestion, and having overall 24/7 reliable baseload capacity that can be built quickly and located almost anywhere. We strongly believe that the FMR is the reactor that best meets the needs of the distributed market, with a demonstration targeted before 2030 and deployment by the mid-2030s. We are seriously committed to that. Again, we will be working closely with Framatome and others to realize these goals. The helium-cooled FMR has multiple key advantages that I'm sure we're going to be expanding on today in the discussion that make it clean, community-friendly energy source. We know that the grid operators want fast response to help address for the variability of renewable. The direct helium breaking cycle of the reactor, GA unique permanent magnet generator, and the GA frequency converter enables a 20% per minute power ramping rate for load following and high overall efficiency of 45% during normal operation. The highly automated control system reduces the burden on the plant operator and allows for efficient grid operator dispatch. We also know that the customers would very much like fast construction for any location, especially those hard to get off grid locations. The target construction period of 24 months will be achieved by employing truck transportable size components, module factory fabrication and standardized plant layout. Also, being dry cooled, the FMR can be sited and installed quickly at geographically diverse nodes and off-grid locations without the need of large water source. Future customers also would like to see a comprehensive yet rapid or fast licensing process. You notice the theme here is all fast. The defense in depth design, passive safety, low source term, low power density, and emplacement below ground are strong design features for utilities that facilitate public acceptance and licensing by the US NRC. The demonstration unit will be licensed under 10 CFR 50, followed by commercial units under 10 CFR Part 52, or the planned 10 CFR 53, if that is going to be out. Finally, customers want confidence that the technology will work and work well. This is really important for all of us. Key technical features have been specifically selected to provide that confidence. The fast neutron spectrum allows for long burn fuel cycle of up to 9 years of operation without refueling. The fuel is UO2, or uranium dioxide fuel, widely used, known fuel type. Silicon carbide composite is used for cladding and internal structures and is chemically inert in the helium environment. Silicon carbide materials are very well known to GA, as we are building on experience with the accident-tolerant fuel program of DOE, SiC cladding development, on top of years of experience in developing silicon carbide composites for nuclear and other applications. Silicon carbide is exceptionally radiation tolerant, well suited for high temperature reactors. The fast neutron spectrum also transmutes long-lived actinides, and I'm sure we're going to talk about that. And I'm doing a lot of the homework for you here, Jake, into short-lived fission products and allow the use of multiple fuel types. We are committing on making this reactor a reality and provide this game-changing, community-friendly, safe, and distributed resource for the 2030s US power market. I would also like to add that we have gotten interest from major utilities in making this a reality. Thank you very much. I look forward to the discussion.
Awesome. Thanks, Ron. Very flattered that we get to hear about that news here. So thanks for sharing that with us. Very exciting indeed. I think real quick, as we jump into this, I just want to let everyone know who's attending. For those who haven't attended past Fast Reactor webinars that we've done, we try to do this in a little bit more of a dynamic fashion. You obviously got the quick intros from everybody. We kept those relatively quick and brief so that we could get into the dialogue. We try to make this much more of a roundtable type chat, even though we're all obviously virtual at this point. But I think it creates a much more organic and dynamic conversation. That said, please start typing in your questions in your Q&A. We'll see those, we'll be able to integrate them and loop them into the conversation and answer them as they go. But to start, Ron, even though you just got to go through that, what I wanted to do is actually kind of start with you and have you talk a little bit more. Obviously, it's pretty exciting to hear about the FMR. I'm curious, can you elaborate a little bit more on why you elected to go with a fast neutron spectrum? What about fast neutrons makes it a compelling choice?
What I think for us is the long fuel cycle that it can afford us, the multiple fuel types that it can be fed, and the really nice solution it has for nuclear waste. I think it's kind of a common feature for many of our designs. Gas fast reactor really offers this additional safety features of inert environment and easy operation and maintenance of the overall reactor system. So that in a nutshell, and I kind of went through those and some more, are what really excites me about the fast spectrum type reactors, and especially what we're working on.
I completely agree. I think that's one of the neat things you can do with, well, one of the many neat things you can do with fast neutrons is what it does for fuel efficiency and fuel utilization. It also opens up a variety of material uses, like you talked about, Ron, but I kind of want to punt that off now to Paolo. Have you talk a little bit about what led you to use fast neutrons? Obviously, there's a physical reason, but it might be useful to have you elaborate on it, especially with what it enables with the lead fast reactor.
Yes, and this is definitely a good and interesting question. But I would, turn it around a little bit in the sense that from our perspective, when we did the evaluation that I mentioned to you earlier, we didn't want to necessarily explore and then develop a fast reactor. We wanted to have, first and foremost, a reactor concept that is economically competitive, even in the most challenging global market. And right now, the most challenging global market is probably the US. In that evaluation, we considered many criteria, and some of them were ranked very well by a fast reactor, by a fast spectrum reactor. An analogy that I often tend to make is between if you need to buy a car or a car that can fly. Right now, if you have a car that can fly, probably you cannot fly simply because of the regulations and the boundary condition don't allow you to do so. However, in 10 or 20 years, these boundary conditions may change. And so why buying a car that cannot fly when for the same price, and in our case, for even better economic performance than conventional reactor, you can have additional capabilities and favorable attributes that are enabled by the operation in fast spectrum, which can become can address needs of the future market. I think one aspect that is common between all of us and also many other people, even outside the nuclear field, is the need to decarbonize the economy and essentially to address global and climate change. So because of that, we can definitely envision, and we have some justification to anticipate an increase in the nuclear share of electricity. If that materializes, some capabilities of fast reactors, so everything that is related to flexibility in fuel management and the capability to close the fuel cycle and to increase tremendously the uranium utilization will become something to definitely care about, even though they may not be now. So the approach that we took is focus on economic competitiveness of a machine with the vision for the future to make sure that the attributes of the reactor, in our case LFR, can address specific needs of these future markets. To give you another piece of information regarding how much we cared about economics, the very first year of development of the LFR, we didn't even have the power level of the reactor. We ended up with a 450 megawatt electric LFR driven primarily by economic considerations. So we took approximately 1 year to understand, to document, to justify why we have a specific power level. These combined with other characteristics of fast spectrum reactors, reactivity coefficients, favorable reactivity coefficients, which tend to promote plant simplification from the standpoint of safety system, were all conducive toward an economically competitive machine. So it is a combination of favorable attributes that made us decide to start exploring and now developing LFR technology.
Great, Paolo, I appreciate that. I think that brings up a good question that I kind of want to dive into here in a minute, but first I'll just jump over. Don, could you talk a little bit about what it is about fast neutrons that led you to get into it? What drove you to that?
I think basically it has to do with the prospect down the road that Paolo talked about, that there is going to be a need to close the fuel cycle. And I joined a situation where we had a team that had been involved in a good bit of their professional lives running, designing, developing, and running the EBR-2, and where they had basically perfected the pyro processing process and knew all about the inherent safety of liquid sodium combined with the zirconium metal fuel. And that, so there was not a lot of thinking about whether fast neutrons were an option. They were always part of our program. And basically, they, in our view, it's not going to be tomorrow, but that's the reason we're not going to fuel our reactor with reprocessed actinides on day one. But sometime during the next 20 years, the value of a closed fuel cycle, together with waste management, is going to be an important attribute and one that's sought. That's what we're betting on, and we're betting on that the proliferation resistance that you'll get will allow you to go into a lot of markets where, with IAEA programs in place, which is where the real demand is for the future. I mean, you have people living on kilowatts per day, and they're not going to sit still for that forever. And I think that's my thinking. The fast neutrons were part and parcel of our design. I can't say I'm a nuclear physicist. I'm a businessman, and I didn't design it. We have seven or six or eight PhDs on our team. They can tell you a little bit more about the cross sections and so forth, but they're a very important part of our design.
I appreciate it, Don. Definitely appreciate that. So Jeff, I'll punt it to you, but I'm going to add a twist in with the question for you that others can pile onto. So obviously you're pursuing this technology, not just because it's cool, but because it has a potential, right? Everyone on this panel is doing the same thing. We're not just doing fast neutrons because we like fast neutrons. It's because we see they have clear potential in terms of economics, because that's what drives everything. We heard Paolo talk about it. We heard Ron talk about it. We just heard Don talk about it. Jeff, can you talk a little bit about why fast neutrons first and how that translates over to the economics? And the reason I think it's important is there's this kind of prevailing mentality. We've seen questions before around, oh, well, fast reactors are just more expensive than LWRs. It's kind of a mythology that often is, tied to many of the other mythologies in nuclear about just doing things the way they've been done because that's the way they've been done. The reality is, right, those data points are typically derived for test reactors and research reactors. So driving that forward to commercial, I'd like to hear you talk a little bit about that. And everyone should feel free, if you guys want to jump in after Jeff, to expand on what he talks about in terms of how you see the economics playing out on this. And one question I'll just flag as part of this too, Jeff, I'm piling it onto you, but obviously economics are important, but the other aspects of, one thing for economics that some people think about with fast reactors is you need more fuel to start a fast reactor. How does that play into the economics? So with that, Jeff, feel free to fire away. So Jeff, you're on mute real quick, if you wouldn't mind.
Thank you. Hopefully it won't happen again.
No
yeah, definitely interested in working on cool stuff, but I was working on laser fusion, so that was already pretty cool. But switching over to something that can have more of an impact sooner, that's what this is about for us. We started work on the molten chloride fast reactor in late 2012, early 2013. And of course it was dark. We didn't announce anything about it for another couple of years after that. Basically one of our black projects, if you will. But by the beginning of 2014, we were already starting to work pretty closely with Southern Company. And so we got that customer influence very early in the game. And so we paid a lot of attention to the economics, to the right way to size it for their grid and other customer considerations, O&M, a lot of different aspects. And so the economics, we've seen a lot of information. There's been the MIT reports, there's been EPRI reports. We get information directly from Southern and other partners. And I think we all know that if you can't hit $3,000 per kilowatt electric, you probably aren't going to have a role in most markets. Certainly the large markets. There's always niche and small scale opportunities, but that's really kind of where the bogey is. We started off with we called it a system design and costing study in 2015 that we were doing in concert with Southern to try and understand the economics of an MCFR. And frankly, we didn't want to be working on it if it wasn't going to be attractive. It just wasn't worth our time. We'd move on to the next idea, and certainly we had plenty of interesting ideas. We were in the middle of that when the 2015 ARC call for proposals came out, and we shut the team down and diverted everybody to work on that, and then ultimately we won that award. And so we're now building the integrated effects test, which is roughly a megawatt of electrical heating to simulate some of the reactor core environment aspects in the form of about a 50-foot on a side machine that we're building up in Everett, Washington. But that economics has been there from the beginning, and others have already touched on this, so I won't dwell on it too much. But the neutron economy, the ability to look at alternate fuels to help close the back end of the fuel cycle, offers a lot of different opportunities. But ultimately, it comes down to the technology. Does it have a shot at hitting those sort of numbers? And we've had other systems where we've had a lot of experience with them that are relatively well developed, but the economics have proven to be pretty challenging. And so that's a big part of the reason we went in from the get-go with that, one of our chief considerations.
Excellent. Go on. Sorry.
Yeah, I could jump in. Well, I think one of the advantages that we see in the gas fast reactor system, for example, is really achieving the highest efficiency which we get. Right now, light water reactors, the existing fleet, is around 33% efficiency, Rankine cycle, steam cycle. If we go to systems that offer you direct conversion of the neutron energy into electricity, which we can do with the Brayton cycle, for example, in this inert system such as helium, you get up to almost 50% efficiency of these systems. That's a game changer for the nuclear industry. I think they're shooting for higher efficiency, given the higher costs associated with the initial implementation of nuclear. But I would go further that we need to shoot for less than $3,000 per kilowatt as a bogey. I don't think that, in the future, things are going to become much, much cheaper. Renewable systems, everything else that is around us is just going to get much cheaper. Economics is king and market values is king. So we also need to look at fixed O&M costs. I think targets for that should go low, and that has to do with autonomous controls and simplicity, modularity, deployment of the systems in a very easy to go kind of way. I saw a question online approaching and asking about the light water lifetime approaching 80 years. There is some confusion with fuel cycle versus lifetime. I want to emphasize we are all designing our reactors to 60 years or longer in lifetime and expecting license renewals after that. The fuel cycle, just to mention to people, that I mentioned 9 years for ours, means no replacement of fuel for 9 years. So that goes to the initial amount of fuel that you put in. It can be large or small, depending on the source term, on how much fuel you need to begin with. But that stays there for many, many years. So it all kind of plays out in this holistic view of what needs to be done to get the economics to where it is competitive, not necessarily now, but down the line when we need the electrons and the applications of the heat that are possible.
Appreciate it. That's a great point. It's a great point, Ron. Great several points. I guess the kind of the question then, you guys hit on, I think generally speaking, talk about how there's different aspects to the potentiality that fast neutrons allow for, including a combination of different approaches, technologically speaking. I'd love to hear you guys talk too about what is a key, I would say, benefit, but also contrast that with some of the challenges of basically being US-based developers compared to some of the international competition. And the part of how I ask that is kind of under the I would say the guise of recognizing that looking at this panel, which is a snapshot that spans the different types of fast reactors under development, but a snapshot of the developers working on them, shows that there's a lot of innovation, right? And I do think that's one of the key competitive advantages in America is our innovation ecosystem, especially in nuclear, that we see really burgeoning. I'd love to hear you guys all talk about that. Ron, since you guys just kind of launching this, can you talk a little bit about that as you're setting out on this? And then I'll jump it over to Don, because given his experience looking at Canada as well.
Well, the international market, I mean, can be extremely aggressive. I'm really looking at our real competitors, which are China and Russia, with their fast track technology approach for everything that they do, state-owned enterprises. It's tough. It's tough to compete with a model like that. I think that there's good ideas there, but at the end of the day, we have the gold standard in this country. I mean, if we're going to license any of these types of reactors in this country, demonstrate economic viability and performance, we can make the world market as well, not just here in the US. So I think there is something to be said about the experience that we have as American industry. I mean, GE, for example, a wholly owned American company, privately held, have been surviving for many years, many decades, building on this gold standard innovation. And I think every single company around this table is viewing it in the same way. So I think Canada obviously offers us interesting opportunities in the future. I would put it at the same kind of range of the decades. And they would also love to host SMRs and reactors such as ours in the future. And a lot of people are applying for their kind of process of doing that. But I really see state-owned enterprises around the world who can benefit from interesting financing schemes and licensing pathways that would challenge us. But I think that if we demonstrate it here and show that it's economic, money is money everywhere. If we can hit those targets, we're going to be successful.
Can you talk a little bit about that? Yeah.
I want to chip in one thing. I think that we're going to have to figure out how to deal with the customer's waste stream. The Russians in particular have got a take back scheme that is not legally possible here. And there are going to have to be models, new models of developing how a customer can deal with its waste. And not everybody wants to try to find and create a Yucca Mountain. They will be very tempted, particularly in the developing world, where we think the most demand is going to be resulting, to creative solutions. And one of the things our team has looked at and has studied a bit is to set up regional processing centers where a core can be taken, reprocessed, and delivered back to the customer. And if you are dealing with a breeding ratio of about 1, each core that's developed is cheaper than the one before. And that's the other aspect of the fast spectrum. I'm not sure where it's going to go. We have a 20-year fuel cycle, as I said, and we're assuming that the innovations are going to occur over that period, but that's basically the business plan. And if you're in Canada, Canada is having some of the same issues locating an acceptable to the public waste management system. They've been trying for a long time. Effectively, it's still stored basically on plant sites, just like it is in the U.S. And there is increasing public resistance to the siting. But I think the U.S. industry is going to have to come up with a solution that works for these other countries without obliging everybody that buys an American reactor to come up with their own waste solution.
Appreciate that, Don. I do think that's an important change here. Go for it, Paolo.
And maybe, Jake, if I can add something regarding international markets and international scenarios versus US. I think one advantage is a double-sided type of sword, but one advantage that we have in the US is that there is a lack, of course, of state-owned enterprises. And this, to me, drives competition. And competition drives innovation and efforts, and more efforts to make this design competitive, and basically to make sure that they have the attributes that are required to address the needs for the markets. So it is more challenging for us. I think from time to time, I would like to be part of a state-owned enterprise, but at the same time, I think it drives innovation to the benefit of the technology. And at the end, the technology can be exported. So I think, as I said, is a double-sided type of sword.
I do think all these fast reactors have really good potential to go international, but it seems pretty clear that starting with U.S. demonstrations is very much the way to go. It's unfortunate, of course, that right now the answer seems to be maybe 2. I think there's good argument to be made that 5 or 6 might very well be in order if you want to ensure that you get it done. It's kind of too important of a problem not to get it done and done well. So hopefully we'll see growth, but it's great, the amount of increased attention that the community's gotten, over the last couple of years, obviously culminating now in ARDP selections. Very exciting time.
Jeff, Jake, can I add just a bit? I think Jeff is making a really important point. I think that goes to the pipeline of innovation in the country. I think sure that we line up the concepts that make sense for market applications and economics, and let the market make those decisions. But the partnership, as you said, through the ARDP and other programs, other forums that the DOE, funding opportunities that DOE has, are really important to keep innovation live and well in this country, and make sure that we hit the final mark into the 2030s.
That's great. I really appreciate that commentary and conversation. I think that's very illuminating to the different aspects and opportunities. I think it brings up a good question here then is, one thing we just talked about was kind of the the benefits on this, let's talk a little bit about where we kind of are in the sense of what are some of the different engineering materials, I'll call them challenges and opportunities that we're looking at, and where on our roadmaps are we all? In other words, as you guys look at where you are, what's ahead of you, and then what should we be expecting in the future, as much as you feel comfortable to say, obviously, but looking forward, you talk about demonstration timelines. It'd be great to talk about what you guys are thinking about in those lines, and any other interim developments you think are exciting to share.
I can start. We are really excited about the materials advancement in this country. We are not back in the 50s or 60s when LWRs have been started. The whole reason that we are here, all of us around the table, is because we have made tremendous advances on materials and fuels. We really like to hybridize experimentation with modeling and simulation. This country invested a humongous amount of efforts and money in advancing computing science and advancements in predicting a priori how things behave, how materials behave, under prototypic conditions even, through then validation with experiments. We are excited by this approach of accelerated fuel qualification that GA has been spearheading with others in the labs and other industries actually that are joining the table on that, to bring modeling and simulation to a point where it can help us target experiments, integral experiments, to reduce the number of years that it takes to qualify new fuels and eventually new materials. So high temperature materials, radiation resistant materials, things that would really work in the harsh environments that we're predicting for higher temperature performance and higher efficiency, to bring this to the 21st century, well into the 21st century, has been gaining a lot of momentum, and I'm really, really happy to see all of this activity.
Great, excellent.
If I could jump in, so in the case of TerraPower's MCFR, something we've emphasized from the get-go is real-world material studies and experiments. And there are, I don't know, 30 startup nuclear companies out there, and for whatever reason, about half of them seem to be molten salt. And unfortunately, there are folks out there who, seem to think that everything we needed to know, we knew, at the culmination of the MSRE in, the 60s and early 70s. And they haven't done testing. And unfortunately, there has been, significant atrophy of capabilities. Oak Ridge, really had wonderful capabilities at the time, and these things need to be recreated. And I don't think that's unique to salts. That's SFRs have similar issues. Lots of technologies do, but you got to get in the laboratory and you got to be actually testing things. You got to fail, and then you got to move on. In our case, we've run over 50 flow loops. We've got about a loop decade of flow experience in doing this, and we've actually found that by taking good care of the salt. Salts have a reputation of being corrosive, but if you actually take good care of them, they take good care of you. And so we've been primarily focused on code case materials. So we're not having to go to fancy materials. We're the integrated effects test that I mentioned earlier, as well as the molten chloride reactor experiment that we hope to build in the next few years and actually turn on. They're both 316 for the structural material, possibly with cladding. In the case of McCree, but the integrated effects test is straight 316, and so we don't have to have massive materials advantages in order to make this work.
And I definitely echo what Ron and Jeff said regarding the importance of materials. In the case of the Westinghouse LFR, we are currently at the end of the conceptual design phase. And we are starting a very important program, mostly experimental in nature. Recently, we received a quite sizable award, approximately $13 million from the UK government. The UK market is currently our, let's say, near-term focus. And this program will be primarily devoted to demonstrate materials, component systems for the LFR in prototypical conditions in terms of liquid lead at prototypical temperature. An important aspect and an important area of that program is corrosion protection and the capability to develop and to test materials that can withstand operation in liquid lead at the temperatures that we want. There is a general, let's say, belief and association between lead, but also molten salts and corrosion. When I generally get that question, and I saw in the QA, there is one question about corrosion, I generally say that there is no doubt in my mind that we can demonstrate and operate safely and reliably an LFR. But that is not our goal. The goal for Westinghouse, which is the next step in the development program, is to demonstrate that we can operate an economically competitive LFR, which means an LFR that operates at a temperature that pushes a little bit the boundary and the status quo of LFR technology. So this is why currently we are putting emphasis on materials development to validate some assumptions that we made and that are essentially the focus of our business case, which is very much related to what Ron said earlier about the importance of efficiency for the economics of the plant.
You know, I want to build a little bit about what Paolo and Jeff said, and Jeff, especially you said that, you know, you're using stainless steel, and obviously we are also given that. So I think the point is we don't want to stay away from conventional materials if they work. If they work, employ them. And that's what we do for the GFR that we, the gas fast reactor that we have. That's what, you know, TerraPower is doing for theirs. If it works, use it. And if you need specialty materials, they can be de-risked and they can be shown to work. It's just a process. We have to build a safety case. In nuclear, that is a must. And in order to get there, that could take some time, but there are innovative ways, like I just mentioned, to get there faster with the technology that we have now, especially with the computing power, the testing facilities. God knows we need more of those, but we can get there even with what we have. I mean, the versatile test reactor would be wonderful to have, especially as a tool to get more of this data. But absent that, we can also, you know, we can get there. We make things quicker, for example. That's an example of a tool that can make things much better.
I might add one thing that hasn't been touched on, which is everybody should think about the importance of the first mover advantage. And a corollary of that principle is that the more you make of a product, the cheaper it gets, irrespective of what it is. We're talking about modularity and getting our products in the market, getting them produced quickly and in the hands of a number of customers is exactly what's happened with wind and solar, and it needs to happen in this industry. And I think we can't lose sight of that. Fine tuning the materials and all. At some point, you pull the plug on the design and get it in the market and start manufacturing it and get the advantages of the economies of scale.
Don, but I have to say, I mean, would you agree with the statement that wind and solar got a lot of help in getting to where they are?
They got about $50 billion from U.S. government after they shut down the sodium fast reactor program in Bill Clinton's era.
So we have to keep that in mind, that without partnership like that, you know, and this is happening now more and more. But I think that's really important to keep in mind.
It is.
I think that's a great point. You know, obviously, as we talk about what a lot of the work has been focused on in terms of federal support on a lot of R&D. I think there's work looking at demonstrations. And one thing I've been trying to, you know, look forward at, and I think is really important we get into is looking at how we support that deployment. Because just like you said, there's a ton of help given to help support and facilitate the deployment of technologies in the renewable space that really helped drive those cost curves down. I think we can expect the same thing for advanced reactors. So I think it's really important people recognize the value that they provide and sort of help accelerate that commercial drive down. One thing to me that I think is kind of an important piece here, oftentimes, you know, there's a tendency sometimes to think groups that are, I think, outside of nuclear look at what projections for nuclear look like. Sometimes those are somewhat pessimistic or cynical, or maybe just sort of flatlined. I think why we're working on these technologies, everyone here, is because we see the broad potentiality for advanced reactors at a truly transformative level on a global playing field, on a global market, to help bring energy to the billion folks who don't have it, as well as the billions of folks who are driving development in their economies and their countries respectively, as well as decarbonizing, right? It's an audaciously difficult, daunting problem. And I think one of the key enablers for that are fast reactors. And one of the things that touches on that, you guys gave great discussions on those different pieces, but I'd love to hit on real quick about the fuel benefits and the fuel cycle benefits. We talked about it. I want to go back to that again and make sure we kind of hit on a couple different aspects of it, as well as how that ties into the economics of it. In particular, you know, how we can actually extend the effective energy we can get out of fuel, out of the raw uranium and even thorium we get out of the ground with fast reactors, but also, you know, how that ties over into the economic benefits of it and the global scalability from a sustainability perspective, but also how that ties in with the sort of safeguards and security considerations, as well as non-proliferation considerations. So, you know, Don, you talked a little bit about that. I'd love to just kind of punt that back to you, given that you guys are looking at this as a key enabler for your technology. Can you talk a little bit more about how that can work and why that's so important in terms of what you can do with fast reactors and recycling?
Thank you, Jake. There are interesting economics. If you look at a 20-year core, there's a lot of uranium, like in our case, about 24 tons. And the piece that's expensive is the enriched piece. We're at about 13%. And if you have a breeding ratio of 1 after 20 years, you've got a lot of your uranium-238 that's turned into actinides, a good bit of it plutonium, but all the others. And with a fast reactor, you can do a simple chemical separation, pulling out the fission products and put the rest of it back in, so that your next core, instead of costing you X, is going to cost you probably a half or 30% of X. The same way you go. Pretty soon you're taking the place of your Inco, and you're generating your own enrichment, and that at the same time you're not paying anybody to haul it away and store it. The economics are pretty compelling.
I think that's a great point. What about, go on, Ron.
Just with reprocessing, we don't just have wet reprocessing, we have dry reprocessing that has been done in the past. So there's all kinds of interesting things about it, but I think the length of the fuel cycle, I mean, the amount of time that this stays in the reactor, that's really a unique feature of the fast reactors. And that's economics. I mean, that's economics, 101. So I think regardless of whether you do reprocessing or not, and I think there's lots of benefits of doing it, closing the fuel cycle like that, you still get the benefits of that fuel cycle that the fast spectrum reactor really offers.
So, Jeff, go for it. You just unmuted. I think you're going to say something.
Sure.
Good.
Yeah, just kind of echoing what the others have said. You know, in our case, there's most certainly a range of options. You know, at one extreme, you know, where I started with the MCFR was, can I make it into a TWR? You know, a breed and burn system, depleted uranium feed after initial startup, and if that's the option that the customer wants, that very much does work. There are, of course, also once through options, which still get a lot higher burn up than you would get with an LWR. And then there's the close the fuel cycle option where you actually look at use nuclear fuel as the input to an MCFR. And I suspect the others all have these range of options as well. It's pretty obvious with the neutron economy you get with the fast neutrons. So yeah, we look at them all.
Is really the flexibility of the fuel management enabled by fast spectrum that is very appealing. I mean, customers now, they are very diverse. In the future, they will be diverse. They will be different from now. And so having a machine that can provide different fuel management capabilities, open, closed cycle, long cycle, short cycle, is an added is a bonus. It gives versatility to the machine. And right now, I think that the energy markets, they don't want to have electricity sources that are too stagnant and too, let's say, boring. They want something that has versatility inherent in the technology itself. the nice thing about fast reactor is that we don't have to be, let's say, smart. Or yeah, I mean, of course we need to be smart, but the technology itself and the physics itself help us and is conducive to reach certain objective when it comes to fuel management flexibility, when it comes to inherent safety coefficients. We don't need to do anything. We need to support the physics. We need to support the nature, but nature already does by itself its role. So it is a significant help that probably, I wouldn't say light water reactor developers don't recognize, because as Westinghouse, I'm one of those, but it is a benefit that may not be fully appreciated by whoever has dealt with thermal spectrum reactors for their entire life.
It's a great.
I might say one more thing we haven't touched on, the notion of inherent load following and the extent to which you can build that into your design by virtue of the reaction of your fuel to changes in temperature. And I think that there's a lot of promise there. We have ideas about this, and we're studying it. But to the extent that you can get your fuel to respond with reactivity change to changes in temperature, you get a perfect circle where you have, when the grid is drawing heat from the coolant because there's a heavy load, the coolant comes back into the reactor cooler. The fuel then becomes more reactive, and vice versa. So the same phenomenon that gives you inherent safety through negative reactivity can be harnessed to give you load following. It's not clear exactly how fast it is. Different people project different things. I think that's not been fully explored yet. We studied it with mathematically, but until we get one going, we probably won't know for sure exactly what the ranges are. I'm talking about load following that doesn't have anything to do with the balance of the plant.
Yeah, I could comment there. Absolutely agree. In the case of the MCFR, our negative temperature feedback's about 20-25 times stronger than a sodium reactor has. Just, density is king in this regard. Something we've proposed as part of pretty much the centerpiece of our ARDP proposal, we went for risk reduction, by the way, is a thing we call the molten chloride reactor experiment. And so we've been working on this now for about a year, including with, of course, folks at NRIC and elsewhere. And this would be a plutonium fueled machine to specifically demonstrate the very low beta that we get both with plutonium as well as with a molten salt, where of course the fuel is moving outside of the core. So you have fewer neutrons to control. The modeling says this will be incredibly stable and a very well-behaved, very nicely load-following machine. Obviously, you want to prove it in an experimental platform, and so that's something we're excited about and think we could probably do in about 3-4 years.
Jake, are we about done soon? I just want to make a comment.
Yeah, what I was going to do, feel free to make a comment, Ron, and then I was going to run around kind of a wrap-up conversation for everyone, and then close out.
I'll do my wrap-up. That's the comment I had.
Perfect. Yeah.
Thank you very much. I'm helping you out, Jake. Thank you very much for this opportunity. This was a great discussion. I mean, we need to do this more often, more frequently, and vary the participants to give an opportunity for everybody to voice their opinions. And I think we all reinforce each other. I would say everything needs to be customer driven to be successful. What does the customer want? Can you deliver it on time? Can you deliver it economically? Do you have the finances? Do you have the licensing required? And it is customer driven. Once you identify who you are catering to and why does it make sense to sell your reactor to them, I think a lot of these kind of fall into place in terms of your of what you need to deliver and how. So that will be my closing remark. Always be cognizant of this is a customer driven market at the end of the day, and we need to provide it. Nuclear is a means to an end because it's so good. I think we all believe in that, in the clean energy production of nuclear. But at the end of the day, we need to make it also. So every one of us can apply for different market segments or all market segments or whatever you want to define it, but listen to what customers want.
That's a great point, Ron. So I think that's a good transition into just kind of run down the panel, and we'll go to Paolo, Jeff, and Don. But I think that's kind of a key thing here is seeing this group of everyone to get together is pretty exciting, and hearing the conversation shows what that diversity of interest and technology spaces look like, with the huge amount of potential that all these different approaches can have, both domestically and internationally. So appreciate that commentary, Ron. Paolo, you mind kind of putting in your wrap-up thoughts, and
Yeah.
feel free, by the way, if you all want to interject a little bit on why you personally are spending your time working on these technologies, that's also helpful.
Yeah, this is a great panel. Maybe something that I wanted to remind everybody is also the importance of recognizing definitely the benefits, but also the challenges. I generally say that nobody should believe a developer if we only talk about the benefits of the technology. There are definitely some challenges, like all the other technology which we should realize, and which we should try to address with the best of our capabilities. Utilizing technical capabilities, leveraging collaboration, domestic collaboration, international collaboration as well. So I think that is one key point. Another point to close is to understand the importance, and always keep in mind the importance of economics and what factors weigh and contribute the most to the economics. These factors may or may not be those addressed by fast reactors. So I think it's important to keep that in mind. There may be, and for sure there are, some components of economics and of capital cost that are not driven specifically by the neutrons being thermal or fast, and they are driven by other characteristics of the plant, which may benefit from inherent characteristic of the technology that we have, from the coolant, and the type of neutron spectrum may or may not play a role in that. Definitely, when it comes to fuel cycle, the neutron spectrum is the king. When it comes to economics, it may or may not be the king.
Appreciate that. Jeff, do you mind kind of sharing your wrap-up commentary?
Sure. I don't want to duplicate too much, but I'll say that I agree with the vast majority of what Ron and Paolo just said. We've certainly, from the get-go, been paying attention to the customer and the economics, and it seems clear to me that the technology has a good chance of working and has a very good chance of being cost-effective as well, and that is paramount. I think I can leave it there. I don't need to take up too much more time.
Jeff, eloquently said. Don, you want to finish this off, and then I'll just.
I'm not sure I'm going to give an elegant finish, but I would say that we do have a customer, and so we have to be responsive to it. It's given us money and expecting us to be online in a time frame they've given to us. So that's kind of where we are.
That's pretty eloquent.
Yeah, very eloquent. Okay, well, first, thank you all. Thank you, Ron, Paolo, Jeff, Don, for joining us today. Thank you for all the attendees who came in. I think this was a great discussion. We'll definitely have more of these. For those who aren't aware, we've had 2 previous Fast Reactor webinars in the past. They are posted to our YouTube channel under the Fast Reactor Working Group, as will this one be. This will be posted here in the coming days. So folks can be able to check it out and watch it at their leisure again if they want to sort of rewatch it, catch some things, or folks had to hop off at different times here. So again, thank you all for everyone being here. We'll be having an announcement for our next webinar here coming up in the coming weeks for the announcement. And we'll be continuing the conversation threads that we've started over the course of the past few webinars. But at the end of the day, as you can see, fast neutrons will play an incredibly important role in terms of how we decarbonize and energize our world. And so thank you again to the panelists, and looking forward to continued conversations going forward.